Welcome to this explainer. Today we're jumping straight into the hidden mechanics of floating and sinking. We're going to look at those invisible forces that dictate why some things rest so effortlessly on the water surface while others just plummet straight to the bottom. If you've ever stood at a harbor and felt a genuine sense of awe at the sheer scale of modern engineering, well, you're definitely in the right place.
So let's start with a puzzle. Think about this for a second, because it really seems to completely defy logic. How exactly does a massive 100,000-ton steel cruise ship float perfectly on the water when a tiny 5-gram steel nail dropped into that exact same ocean sinks like a stone? I mean, they're both made of steel, right? The ship is millions of times heavier, and yet the heavy one floats and the ridiculously light one sinks. Why on earth does that happen?
Well, it all comes down to how they're built. On one hand, we've got our massive cruise ship. Sure, it has a ridiculously heavy steel hull, giant engines, and thousands of passengers, but crucially, the ship is essentially a hollow shell. Inside that massive shell is an enormous volume of air. On the other hand, take our tiny steel nail. It's incredibly small, it's light, but it's a solid, totally compacted block of metal. This right here is absolute proof that weight alone doesn't determine if something floats or sinks. There is a much deeper principle pulling the strings here.
Section 1. Archimedes and the Bath, a eureka moment in 212 BC.
To really solve this paradox, we actually need to wind the clock way back. Let's head to 212 BC, to the ancient city of Syracuse. There was this brilliant Greek scientist named Archimedes, and he was wrestling with a pretty tough physics problem. Legend has it the answer hit him right as he stepped into a public bath and watched the water level rise and spill over the edges. He was literally so excited by this realization that he supposedly ran totally naked through the streets, shouting "Eureka!", which means "I've found it." What he discovered is what we now call Archimedes Principle. It states that the magnitude of the buoyant force is exactly equal to the weight of the fluid displaced by the submerged object. In plain English, when you push an object into a fluid, the fluid pushes right back up, and the strength of that upward push is perfectly equal to the weight of the water that just got shoved out of the way.
Section 2. Upthrust, the invisible force. Seeing the unseen pressures.
Now that upward push actually has a name. We call it upthrust or buoyant force. But to really grasp how this works, we need to understand exactly why the water pushes back in the first place. So imagine putting on a pair of X-ray glasses and looking beneath the surface to see the actual forces acting on a submerged object. Water pressure is pushing against it from all sides, right? The pressure pushing against the left and right sides is equal, so those forces just cancel each other out. But think about the top and the bottom. Water pressure increases with depth. The deeper you go, the more weight from the overlying water is pressing down on you. Because the bottom of a submerged object is deeper than the top of it, the upward pressure from below is always going to be stronger than the downward pressure from above. That difference creates a net upward push. And that, my friends, is your upthrust.
You can actually measure this exact balance of forces in a lab. If you hang an object from a wire connected to a scale and then fully submerge it in water, a few things happen. You've got the total weight of the object pulling down, but you've got two things pulling up: the tension from the wire plus that invisible upward buoyant force we just talked about. Because the water is literally helping to hold the object up, the tension on the wire ends up being less than the object's true weight. This is exactly why heavy objects suddenly feel so much lighter when you pick them up underwater.
Section 3. The secret of density, the missing link. Okay, but we still haven't entirely solved our ship and nail paradox, have we? We know upthrust pushes things up. But why is the upthrust strong enough to hold up a gigantic ship, but totally fails a tiny nail? Well, like we noted earlier, weight isn't the whole story. The real secret, the missing link here, is density. The absolute crucial point to remember is this simple equation: density equals mass divided by volume. Just think of density as a measure of how tightly packed the mass within a substance actually is. If you've got a ton of mass crammed into a tiny little space, you have high density. But if you take that exact same mass and spread it out over a huge space, you get low density.
When we look at different materials, fresh water has a density of exactly 1.0 grams per cubic centimeter. Lead is super dense, sitting at over 11. Air, though, it's practically 0. And here's where the magic really happens. Whether something floats or sinks depends entirely on its average density compared to the water. If the object's average density is under 1.0, it floats. If it's over, it sinks. A solid steel nail is just pure steel, which is incredibly dense, so it sinks right to the bottom. But our cruise ship? It's basically a giant steel balloon. Because that hollow steel hull contains a massive volume of super low density air, the average density of the entire ship, we're talking the steel, the engines, the cargo, the air, the whole shebang, drops well below 1.0.
It is technically less dense than the water it displaces.
To show you just how far engineers can push this principle, let's talk about the pioneering Spirit. It's the heaviest ship in the world. This absolute marvel displaces a staggering 900,000 metric tons of water. To put that into perspective for you, that is the equivalent weight of about 300,000 elephants. It's wild to think about. And yet, because of the brilliant engineering of its volume and the air trapped inside its massive hull, its average density stays lower than the ocean, so it just floats there, effortlessly.
Section 4. Measuring the irregular. The lab practice.
So how do scientists actually figure out the volume and density of, say, weirdly shaped objects that you can't just slap a ruler against? Well, we use the exact same principles Archimedes gave us over 2,000 years ago. In a lab setting, you might use a spring scale to measure the apparent weight of a metal block as it gets lowered into a beaker of water. Or you might use a triple beam balance with an adjustable platform doing the exact same thing. By measuring the object's true mass in the air and then its apparent mass while it's submerged, we can calculate the exact amount of upthrust it's experiencing. And thanks to Archimedes, that upthrust tells us exactly how much water was displaced, which instantly gives us our volume.
And another really classic method uses a piece of equipment literally called a eureka can. Shout out to Archimedes. It's super simple. First, you fill the can with water right up to the very edge of the spout. Then, you carefully lower your irregular object, maybe a strange lump of metal or a jagged rock, using a thin piece of thread. The water that the object displaces spills right out of the spout and gets caught in a measuring cylinder. The volume of that spilled water perfectly equals the volume of your object. Just a quick pro tip for anyone trying this in a lab, using a thick piece of string will totally ruin your results because the string itself displaces water. And obviously, spilling any water before it hits the cylinder will completely throw off your math. Precision is everything.
Section 5. Why the Titanic sank. A tragic loss of buoyancy.
So, we've seen the incredible power of buoyancy, keeping 900,000-ton vessels perfectly afloat. But what happens when that highly engineered, careful balance of density is broken? The sinking of the RMS Titanic in 1912 is, tragically, a textbook example of a total loss of buoyancy. As we know, the ship floated because the vast amount of air inside gave it an average density way lower than the ocean. But when the Titanic struck that iceberg, it tore several small holes along the steel hull. Immediately, heavy ocean water started rushing into the bow. As all that water entered, the buoyant, low-density air was forcefully pushed out. Step by step, compartment by compartment, the empty space was entirely replaced by incredibly heavy water. Eventually, it hit a tipping point. The ship's average density, which was now a combination of heavy steel and heavy water instead of steel and air, finally exceeded the density of the surrounding ocean. Its positive buoyancy was completely destroyed. The massive ship became just like our tiny steel nail.
What is honestly so terrifying about a loss of buoyancy is the sheer speed at which it takes hold. It took only 160 minutes, that is just 2 hours and 40 minutes, for this massive, supposedly unsinkable ship to succumb to the cold, hard laws of physics once its density shifted. The ocean itself didn't change, the ship's density did. And once that happened, gravity just did the rest. We have covered a lot of ground in this explainer today, everything from ancient Greek bathtubs to modern maritime engineering disasters. But I want to leave you with one final, kind of mind-bending thought. We learned earlier that buoyancy, that upward upthrust, is created by differences in water pressure. And that pressure difference is caused by the weight of the water, which is fundamentally caused by gravity pulling down on it, right? So, if buoyancy relies entirely on gravity to even exist, does buoyancy exist in the zero-gravity environment of space? Like, if you let go of a wooden block inside a floating orb of water up on the International Space Station, would it float to the top, or would it just sit there in the middle? I'll let you ponder how these fundamental laws of physics adapt, or entirely disappear, when we leave the planet. Keep questioning, keep learning, and thank you so much for joining me on this explainer.